Hey everybody, Dr. Retzik here with you. This is our third video in 7D, and I thought we could just do an example now that we have the polar decomposition at our disposal. Let's get started. So this is a continuation in section 7D. And I have a concrete example here. Example. Let T, a linear operator on F3, doesn't matter if you're visualizing F as the reals or the complex field for this example. Let it be given by T of xyz equals z 2x 3y. All right, so that's a perfectly nice linear operator. It's easy to plug vectors in and see what vectors pop out. In terms of sort of basis matrix representations of this operator, if you just choose the standard basis with respect to 1, 0, 0, 0, 1, 0, and 0, 0, 1, the matrix for this operator T, all right, well, let's just look at it. Where does 1, 0, 0 get sent? That goes to 0, 2, 0. And then where does 0, 1, 0 get sent? That goes to 0, 0, 3. And finally, where does 0, 0, 1 get sent? That goes to 1, 0, 0. Okay, so in terms of the standard basis, that's our matrix for T. Now, because this standard basis here is orthonormal with the usual inner product on F3, then for free, we get the matrix representation for T star. Thus, the matrix for T star, well, if you built your matrix for T out of an orthonormal basis, then the matrix for T star, you just do the conjugate transpose of that matrix. Now, our matrix is mostly zeros and has only real numbers in it, and so the conjugate transpose is just the transpose, and so it's easy to write down. So first row used to be first column. Second row used to be second column. Third row used to be third column. Fast. Nice. So now we have the matrix for T star. Now, just with your eyes, you look at those two matrices and you say, well, those aren't the same. So that's it. T is not self-adjoint. For sure, T is not self-adjoint. So your conclusion right here is T does not equal T star. Okay, so this operator is not that nice. It's not self-adjoint. All right, well, dang. Okay, well, it's possible it's normal. And if it isn't, at least it might be nice to see the matrix for, say, T star T. Therefore, the matrix for T star T is Okay, well, here's T star. Here's T. And when you multiply this out, like in a Math 206 way, you get another 3 by 3 matrix, and it's 4, 0, 0 first column, 0, 9, 0 second column, 0, 0, 1 last column. Okay, now let's pause for a second and get our bearings. First of all, we are not at all surprised that T star T ended up looking like that. We were expecting T star T to look like that all along, because this operator, T star T, even if T isn't nice, T star T is great. T star T, that operator is positive, so self-adjoint. It's got all these eigenvalues, like everything's really nice. And so you say, all right, well, T wasn't that great. It wasn't self-adjoint, but boy, T star T, what a nice operator. We should note right here, if you did it in the other order, if you looked at the matrix for TT star, so reverse the order of that multiplication, you do not get what we just got for T star T. So T is not even normal. So this T, this really benign T that we started with, is not really a very nice operator. In terms of our classification of things. It's not self-adjoint, it's not normal. This T that we started with up here, this is just some kind of outside all of our nice categories operator. All right. Another sense in which T is not nice moreover, original T has only lambda equals root 6 as its solitary eigenvalue. And the dimension of the eigenspace that goes with root 6 is 1. So in a Math 306 kind of way, oh my goodness, T is just not great. T has only one eigenvalue. This one eigenvalue yields only a one-dimensional subspace of eigenvectors. This is a three-dimensional problem. So this T is not diagonalizable. There is no basis for this T, orthonormal or otherwise. There is no basis for this T that makes its matrix diagonal. Nor is T self-adjoint, nor is T normal. This T, it's got a simple formula, but boy, not great. Okay, so T is not great. That's the moral of the story so far. This T is not great. This simple operator is just not great. And yet, we know from the polar decomposition that this T, with no nice properties whatsoever, there is an isometry S such that this T, this not nice T, is S times the positive square root of T star T. So even though T is not nice, T is practically something that is nice. T is practically this. Apart from modification by an isometry, T is very nearly the positive square root of T star T, which is great. So what I feel like is, I want to say something like this. Loosely, T is roughly, now can we think about the positive square root of T star T? Look at, we found T star T up here. Here's its matrix. That's the matrix for T star T. So the positive square root of T star T with respect to the standard basis is this matrix. 2, 3, 1 on the diagonal. So I want to say something like that. That's not a literal equal sign. That is absolutely not T. But man, T is that really pretty matrix modified by an isometry. So T is S times that matrix for some isometry S. Okay, so in that sense, T kind of is sort of nice. And these numbers right here, those numbers give some kind of description of T in which T is nice, and they have a special name. Definition. Given T, a linear operator on V, with no special properties at all, the singular values of T, so that's the term we're defining, singular values, are the eigenvalues of T star T square root. And then can we say each repeated dimension E lambda root T star T times. So if the diagonal on that matrix there, instead of 2, 3, 1 had been 2, 2, 1, then we would list the singular values out as 2, 2, 1, not simply 2, 1. So you always list them out, just by convention, you list them out according to the number of times they appear there on that diagonal. So these things, the singular values of T, they're not literally eigenvalues. I mean, they're clearly not. In our example, the only eigenvalue of T in our example was root 6. And yet here we have these numbers 2, 3, 1. appearing as the eigenvalues of root t star t. So it's not fair to say that every operator has eigenvalues, not true, but every operator certainly has singular values, and the number of singular values of the operator is just the dimension of the space. Because this thing, root t star t, this is definitely a positive operator and is therefore going to have all these eigenvalues down the diagonal with respect to some orthonormal basis. So that's it. That's what the singular values are. Our last video coming up for, what is it going to be? It's going to be Thursday of this week, is going to try to tell us, well, who cares? So what? You have these things called singular values, which are not quite eigenvalues of t, but they're somehow related to t. Why would a person want to know the singular values of an operator t? And the answer is, well, there's a way to decompose t in terms of its singular values. You can get nice descriptions of the operator t in terms of the singular values. And so that's our last big theorem. That'll be coming up in the last video. I'll see you next time.